Let's have some more fun with functions. Here I have two functions defined, f of x and g of x, and the task here is to find the sum of these functions, the difference of these functions, the product, and the quotient. So hit pause, take a few moments, and see if you can come up with these before I go through them. Taking a look at the first one, we have 2 going into F, we have 3 going into G, and then we're going to add the two answers together. So calculating F of 2, we get 5. Calculating G of 3, we get 7. We're adding them together. So the sum of those two functions is 12. So the sum of those two values evaluated in each individual function is 12. You can think of it as we're doing one set of operations. We then do a second set of operations with something different, and then we're combining the two results. Sort of like if there are two groups doing some sort of project and they split the project up into pieces. This group is doing one part of the project, this group is doing another part of the project, and then they get together and combine their results into one final product. That's, in a sense, what's happening here. Next one is a difference of two functions. So again, we'll evaluate f at 2, evaluate g at 3. We already know what f of 2 and g of 3 are. So this time it comes out to be -2. And then we take a product of those two. We get 35. And then last, we take their quotient and we get 5/7. Over here on the right-hand side, I have a similar question. Only now it says find f plus g, f minus g, f times g, and f over g. Let's see what happens here. So now instead of evaluating for a specific value, we'll evaluate in general. So f plus g. F plus g is simply x squared plus 1 added to x plus 4. Collecting our like terms, we get x squared plus x plus 5. This is not a composition of functions. It is not a composition of functions because we are not putting one function into another function. We are merely writing two functions side by side and collecting their like terms. So this is a little different. And we have to be a little careful sometimes when we do this, not to confuse it with composition. Again, this is f plus g. This is not f of g. It is not f of g. Looking at f minus g. Again, we will write the functions side by side, being very careful to subtract correctly. And when all is said and done here, we end up with x squared minus x minus 3. So here's our difference of the two functions. Again, it's not a composition. Not a composition. F times g multiplying this out, we have the following, and then f over g, the simplest one, plus 4. That is the simplest of them because nothing will reduce. This is some function arithmetic. And just to compare, I'll do a composition. F of g of x we would put x plus 4 into f. Rule for f, whatever's inside the parentheses, it's squared, and then 1 is added to it, and it looks like we get this, which does not match any of these up here. So none of these were compositions. None of these were compositions. I'm going to look at one more. I'm going to give f and g the same input. Notice that when we first started this problem, I had two different inputs. 2 went into f, 3 went into g. Let's see what happens if they have the same input. 3 goes into f, 3 goes into g. So when we evaluate f of 3, is that what f is? X squared plus 1. We get 10. Plug 3 into g. G is simply x plus 4. And we get 17. Yeah, we didn't get 17 there. But if I come back up to here, f plus g, assuming I give f and g the same input, what happens when I plug 3 into this value of x? You get 9, plus 3 is 12, plus 5 is 17. I have found a formula to evaluate the sum of two functions if they have the same input. Assuming they both have the same input, these green formulas will provide a shortcut. And just to prove that it works, try g of f of 2 and g of 2. F of 2 becomes 5, g of 2 becomes 6, 11. If I were to plug 2 into this formula up here, 2 squared is 4, plus 2 more is 6, plus 5 more is 11. And we can do that with all of these as well. We could do an f minus g, an f times g, and so on. But the catch is you have to give f and g the same exact input for these formulas to work. Giving them different inputs does not let you use the shorter versions over here. And again, don't confuse these with compositions. This is a sum, a difference, product, quotient. This involves putting one function into another function. Completely different process. In general, if f and g are functions, the sum of two functions is the same as putting one input into their combined sum, just like we did back here. What we did down here at the bottom in blue and what we did up here in green is that first property. This property is equivalent to what we just did on the last screen. The stuff at the bottom in blue would be this. Evaluate them separately. Give them the same value and evaluate them separately, add the answers. This property, what this says is if you add f and g, then you plug in an input, you'll get the same value as over here. So this side of the formula, this side of this equation, this right-hand side, is what we did in green. We added f and g first, simplified it down, then I plugged in the value 3, and I got 17. Plugged in the value 2, got 11. And this repeats with every property. We can do that with difference. We can take the differences separately and calculate. We can subtract first and then plug in a value. We can do that with product. And we can do that with a quotient on one condition. G of x cannot give us 0. If we plug in a value of x that makes the denominator 0, then property number 4 fails. Here is something that we don't encounter much in pre-calculus, but this is something you may encounter down the road sometime. And that's a function of 2 variables. And just to show you that it's not extremely difficult to handle, let's do an example here. So here I have f of x, y. F of x, y. Normally when we have f of x, we've been able to rewrite that and say it's y equals. Well, now we have 2 things going into the function. We have an x and a y going in. So this is no longer a y equals equation. It's what's called z equals. If I were to rewrite this to try to graph, I would get z equals x squared plus y squared. With just regular f of x, we're plugging in a value and we're getting a value in return. So we finish with an ordered pair. With a function like this, we're giving it an ordered pair and we're getting a third value. So we will finish with an ordered triple. And an ordered triple means we're graphing in 3 dimensions. Let's see what happens here. F of 1, 3. Well, the number to the left of the comma gets plugged into this spot. Whatever's to the right of the comma gets plugged into that spot. So I have a 1, 3. This is 1 squared plus 3 squared, which is 10. F of negative 3, positive 4. Negative 3 squared is 9. Plus 4 squared, we would get 25. So if I were to plot these on a graph, here's my x, here's my y, and I just found a z. Here's my x, here's my y, and I just found a z. That's what an ordered triple looks like. Now those of you with a good memory might recognize x squared plus y squared as the equation of a circle. But the equation of a circle is equal to the radius squared. This is a function on this side. So this is not the equation of a circle. A circle is not 3-dimensional. A circle is 2-dimensional. A circle is not a function. So we cannot write the equation of a circle in f of x format. Anyway, violates the vertical line test. So what the heck does this graph look like? If your first thought is sphere, it's not a bad guess, but it's wrong. It's something that you may encounter, in fact, you will encounter if you take a third semester calculus course someday. And that is a paraboloid. That's what the graph of x squared plus y squared looks like. Here's, in fact, what a 3D coordinate plane sometimes looks like. You have your x-axis here, your y-axis here, and now your z-axis is the vertical axis. X and y are on the floor. Think of them as a floor tile where you go left to right is your x, forward and backward is your y, and now up and down becomes z. So this is what a three-dimensional shape called a paraboloid looks like. And it looks like a paraboloid that's been sort of drawn several times in different directions. And it's sort of scooped up so that the top is open, kind of like an egg that's been cracked open. Nice gooey Cadbury chocolate egg. So delicious. Kind of has that feel to it. So you've got this opening here, and then you've got all these little parabola shapes going around the border. You'll learn more about those in Calc 3 for those of you that take that course. Finish up this page. We've seen f of x. We know that's y equals something, and that's going to give us a two-dimensional graph. I don't want to do that. We've now seen f of x, y, which turns into an equation z equals stuff. That's a three-dimensional graph. Well, what happens next? Well, you can keep going. If you give a graph, or if you give a function in order to triple, you would get a four-dimension graph. And I don't recall what the variable is that goes here. I'll just call it W, just because. There's no rhyme or reason for that. I just chose it. So your answer would be an ordered quadruple, 4 dimensions. And we can't really see a 4-dimensional graph because our eyes are created for a 3-dimensional world. We can see 3 dimensions and below. We cannot really see 4-dimensional objects. But mathematically they exist. And we could keep going. We could graph, or at least mathematically describe a 5D function, a 6D function, all the way to however many dimensions we want. There is no limit. So when you encounter functions like this, we treat them the same way we treated other functions. We just plug in the values in the correct spots or plug in the expressions in the correct spots and go to work. Again, those of you that take a Calculus 3 course, Calculus 3 is what's called multivariable calculus, multivariable functions. It's basically Calculus 1 all over again, but in 3 dimensions and beyond. And you learn some really cool things like spherical coordinates, cylindrical coordinates, and it makes certain problems that were pretty messy, it makes them kind of simple. So maybe you'll have the fortune to take that someday. It's a good course. It's not hard, it's just different. Last thing for this video, and this is kind of an important topic because we're going to see a lot of these moving forward. It's called a piecewise defined function, or sometimes just called a piecewise function. And it means exactly what it says. It's a function. Well, I haven't lost my ability to write badly on a board. It's a function that is defined in pieces. For example, I'm going to define f of x to be, I'll just make one up here on the spot. 3 minus x if x is less than negative 10. So whenever x is smaller than negative 10, f of x is 3 minus x. We'll say x squared plus 1 if x is between and including negative 10 and let's say positive 10. So whenever x is negative 10, positive 10, or any number in between, I use x squared plus 1. What about x bigger than 10? Well, I don't really have to include it. Maybe this is all I want to do, but I'll include it. Let's say 2x minus 3, x greater than 10. Notice what I have to do here. Because I have negative 10 in two spots, I have to give it an open circle at one of those spots. So I'm not including it here because it's included here. If both of these are less than or equal to, then I have a problem. Then I've failed the vertical line test. Same thing here. Because I put the equal to bar there, I have to leave it off here. And I could switch those. I could make this equal to and take this one away. It's the same thing. It's just a matter of which value do I want 10 to count with. Okay. Now that I have a piecewise defined function, let me calculate some values. I want f of negative 15. I want f of 3, f of 8, f of 20. Think of this as you've got a bunch of things that have to be sorted, put them in the right pile, or match them with the correct area. Negative 15, x is negative 15. Where does negative 15 go? Yeah, right here. Negative 15 is less than negative 10. So, f of negative 15, when I have a number that is true for this, it gets plugged into this spot. And I get positive 18. F of negative 15 is positive 18. F of 3. Is 3 less than negative 10? Didn't think so. Is 3 between negative 10 and positive 10? Yes, it is. So now I use this. This value of x is true for this section. So here's the rule for those numbers. We square it, we add 1. F of 3 is 10. F of 8. 8 still works here. 64 plus 1, 65. F of 20. Nope, 20 is not between them. 20 is not smaller than negative 10. 20 is bigger than 10. So plugging in 20, you get 37. That is how you deal with a piecewise function. And to see what this looks like on a graph, I'm going to just sketch a kind of sort of not to scale graph here. So x is less than negative 10, we have 3 minus x. So we'll say out here's negative 10. It's going to be 3 minus x. So I'm going to have kind of something like, well, let me use one of my points here. It's going to kind of sort of look something like this. Kind of, sort of. But an open circle there. Because when x is negative 10, I don't use this number. Actually, hold on, I did that incorrect. I'm going the wrong way. That should be up here. There we go. That's better. As x becomes negative 12, y is 15. When x is negative 11, it's positive 14. If x is allowed to be negative 10, then y would be 13. But it's not allowed to get there. It's allowed to get really, 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 really close, but it's never allowed to get there. So that part of the graph looks like this. Open circle, and then here's 3 minus x. X squared plus 1 when x is between these numbers. So this is a parabola. Opens upward. So now when x is negative 10, this becomes 101. So again, I'm not going to get a real good scale here. We'll say this is y is 101. And it's going to kind of look like this. Close circle. And like so. That might not be. No, I need to back up. I need to watch my points here. So when x is negative 10, that would be 101. When x is negative 9, that would be 82. When x is negative 8, okay, I see. So it kind of would look like this. That's better. There we go. It's going to come down. When x is 0, it's going to be positive 1, and then it's going to grow again. There's that part of the graph. And then 2x minus 3. When x is 10, so here's 10 right here. I'm kind of doing this on the fly. Bear with me. When x is 10, it can't be 10 because this says greater than, but let's just pretend it was. Y would be 17. So we'll say that this is, again, not the scale. This is 17. And then notice that we have an open circle. Because we have closed here, we have to pass the vertical line test. And 2x minus 3 would go kind of sort of up like that. There's a graph of this piecewise function. And it's in pieces. One piece is here, one piece is here, one piece is here. You might be asking yourself, where in the heck are piecewise functions relevant? Well, here's an example. If you've ever been to the post office, you have seen piecewise functions. Or if you've ever had different admission criteria, you've seen piecewise functions. Sometimes what I'm drawing here is called a step function because it looks like a staircase. It looks like steps. So let me just pick this one. Let's say this represents age, and we'll ignore all this for a moment. Just focus on the right-hand side here. If you are age 0 to 5, you eat free at a restaurant. Or if you're age 0 to 5, you get into the water park for free. If you are greater than 5 but less than 10, you pay $3. If you are over 10 but not yet an adult, you pay $8. And if you're an adult, you pay, I don't know, $12. Post office uses this. Anything that weighs between so many pounds and so many pounds, here's a flat shipping rate. Here's the next set. Maybe this is, I don't know, 5 pounds to 15 pounds. Here's how much that would cost. Anything greater than 15, less than 30 pounds would cost this much, and so on and so on. That's where piecewise functions are primarily used, when you have different criteria at different times. You have all seen a piecewise function in Algebra 1. The absolute value function. This is a piecewise function. When x is positive, we write it as x is greater than, we just write it as x. When x is greater than or equal to 0, we write it as x. When x is less than 0, when x is negative, we write it as negative x. Absolute value is a piecewise function. So let's check that. F of 3. 3 is greater than or equal to 0. So f of 3, it's just 3. The absolute value of 3 is 3. F of negative 3. Negative 3 is less than 0. So the rule says take the opposite of whatever's inside the parentheses. What's inside the parentheses? Negative 3. There's the opposite, positive 3. Absolute value is a piecewise function.